That's the one you were talking about too. Yeah, he did. At the end, he plugged in 3. Initially, you couldn't, because if you plugged in 3, you got 0 over 0. You can't divide by 0. So if you can't remember them, bless you. Bless you. All right.
Sneeze on your birthday, you'll die.
Dang it. Okay.
That's a rule of thumb, guys.
69. A water balloon dropped from a window high above the ground and falls. Y equals, you know, I like that y'all are more mature than my second and third block class. Yes.
What? Why? We were too distracted.
They've had 23 times 3 on my board every day, and I keep erasing it, and they keep putting it back. It's not on there now, but yeah. All right. Hey. Y'all are full of yourselves this morning. Okay. Oh my goodness. Now we're Van, unit circle, full of yourself. I'm not going to remember all of this. Find the balloon's average speed during the first 3 seconds. So anytime it says average, I know that I am you good? Okay. Anytime it says average speed, my brain automatically should go to AROC, right? And AROC is just a fancy way of saying find the slope between 2 points, right? Rate of change. Y'all good? All right, it says, well, that's part B. All right, first 3 seconds, right? So that means average, I want to take the first part and the last part and average them together, right? So I'm going to go at 0, that's right, delta. At zero, what is T? 0. Now I need to do 3. Now I need to do 3. So at T equals 3, Y equals 4.9 times 3 squared, right? I don't know what that is. I will tell you, get used to on FRQs, you have to take everything out 3 places. That's your rule of thumb. I don't know if this has any more places. Okay, it's probably just 1 decimal. But if there's anything that you have to round, it's at least 3 places. All right. And they will take your answer point away from you if you don't. Like you get 1 point for the correct answer, and then you get so many points. But there's always 1 answer point. You will not get that if it's not rounded correctly.
3 whole places is like 3 decimals.
Say that again. Decimal places. No, what y'all talking about? Digits or like 3 places after the decimal. Well, if it's no decimal, don't put them on there. If it's a whole number, just write the whole number. If this one, that would be fine. But if it was something that you had like some irrational number or something. Then we would, if you have to round it, take it out at least 3 decimal places. All right, 44.1 minus 0 over 3 minus 0. Right? The top unit is meters, the bottom unit is seconds. So what's 44.1 divided by 3?
14.7.
Make sure you include units. That's another, you'll lose that point again.
every single. Well, that's a portion of my middle.
You have to include in every definition your answer.
So you have to say units.
The units that you need,
What if
yes.
you don't circle your answer? That'd be hilarious. So you can add one up.
No.
Oh, really?
If you circle your answer, make sure that's your final answer because that's what they're looking at as the answer for your answer point. You can get a lot of points from a lot of things in FRQs and calculus. That's what I told everybody last year. I don't care if you have no idea how to start the problem, write something. Because you get little points for little things, and you'll see as we practice with FRQs. You don't know how to do anything else, take the derivative of something and write it there. I mean, do something. All right. You will. Don't worry. All right. Part B. So this is average speed, right? That means everybody understands the difference in average and instantaneous, right? Okay, so it averages 14 meters per second. That doesn't mean that's what it's going at 3 seconds. So part B says, what's the speed? Find the speed at the instant t equals 3. But it won't always say instant. They're getting you warmed up to this. It'll say, what is the speed at t equals 3? If it's asking you for a specific time, the speed at one specific time, that is always instantaneous, and you're using IROC. You didn't have to, but it's change in Y and change in X. Yeah. I just wanted to really, really drive home that is what we're doing. All right, IROC. So IROC, you have to remember that formula. This formula we derived it in the beginning and we went through along where I showed you the graph, I showed you what H was. At the end of the day, you just have to memorize that formula, okay? And it does come up because a lot of things will say something like using the definition of or things like that. So you really have to know definitions. And this one's different. This one gives you a different formula. 4.9 t squared. By the way, I had the school buy y'all Barron's books. I'm super excited. Yeah, I know. It wasn't Coach Collins. I told Miss Clyburn I wanted them.
Yeah, Miss Clyburn.
Huh? That's IROC.
Let me look at the difference between IROC.
Okay, so yes, it can. Okay, yes, that can be AROC. But it's IROC when H is going to 0, when H is getting smaller and smaller and smaller and smaller. So when there's no, you see what I'm saying? No. IROC is whenever H is 0. I could use that same formula and know, okay, what's the difference? What would the H be between these 2 points? What would the H be between these 2 points? In other words, how far do I move over from the first X to the second X? 3, right? But if I'm doing IROC, how far do I move over from the first point to the second point? 0, right? It's just showing you how we derive that it is the same formula, but you're averaging no change instead of some change. So that was going from AROC to IROC, yes. But if you're just finding average rate of change, slope. Okay. IROC, though, agree or disagree?
I agree with that. I agree.
Okay. Well, this is just saying, okay, so this is if f of x equals, I haven't planned. So I should actually do this and this. What should I do now? Okay, so 4.9. What? Oh, 3 for t. That's right.
And then make sure you use 1.1.
Yeah.
So you could do this. Oh my gosh. Yes. All right, so depending on, go ahead.
You square the second one too.
Gosh, dog it. This is the formula.
Yes. So the formula is always squared?
I put 3 in for t, so what I did was, really, f of 3 plus h minus f of 3 over h. That's how I got to that. Okay.
From the beginning formula?
Correct. Now, here's where I have to kind of think about this in terms of limits, because I can't have a 0 on the bottom, right? I can't divide by 0. Say right, because that's right. Okay. Y'all are half asleep. Y'all came in with such energy, and now y'all are like,
I'm not half asleep.
y'all are like a deflated balloon.
Right, I'm excited. I had to read an hour and a half and write a little.
It's got procrastinated.
All right, so the question is, as h gets closer and closer to 0 here, what happens? So if I plug in, and if you like to plug in, plug in. If you want to plug in 0.01 or 0.001, or if you want to plug in whatever you want to plug it in. If you want to expand this out and cancel the h's out, and then plug 0 in, you can do that also. It's just a difference in an algebraic solve versus a tabular solve. Yes. Yes.
Okay, that makes sense.
You use that other little formula with 16.
Right, it wasn't 6. That's she's correct. You look at it's the equation that's given. She's right.
So it's pretty much the same except for you use that equation.
A rock is slope. I rock is plugged in this equation with h going to 0. You could use this equation for A rock. Okay, you could. The h in this case from here would be 3. Right? But it's easier just to use slope. It's the same thing though. It's the same thing. All right. Are y'all okay? Okay, so let's do it. I think because I keep doing it both ways, you think you have to do both things, but you don't. It's one or the other. Okay, no. You can't just plug 0 in here. That's what I'm saying. Oh, okay. Let me do it algebraically first. No, Dylan, no. Not both ways. Oh my goodness, y'all. 9 plus 6h plus h squared. Now the reason I haven't multiplied this out, one, I'm lazy. Right here, because I've got 4.9 times 9 whenever I distribute this, right? And there's a positive and there's a negative.
I can tell you what you can do right here.
Is it what the book did?
Yes, I was like, it went from like the first step to that one, and
Slater's not available anymore.
okay, you can put it.
54, right? 54, 24, 59. Is that right? No, that's not right. That's not right, no. 29. I need my calculator. 69. Boop, boop. That's fine. And then also look, H. 29.4 plus 4.9H And then you plug a 0 in, because remember I want 0. So essentially what you're doing here, you're algebraically manipulating it to find the limit just like you did in the other one.
So you can plug in 0.
Yes, once you get, it's kind of like that factor problem that I showed you at the very beginning, where you factored it to cancel out, then you could plug in, same concept. You're just manipulating it so that you can plug in.
But for these specifically, it's the same like format that you do every
Yes, absolutely. Yeah.
So IROC and AROC have the same format. The only difference is
There's no change in the IROC. There is no second point. Yes, that's what I'm saying. It is just the algebraic manipulation to find the limit, so that you can use substitution for the limit. If it's what? Absolutely. Slope, yep. Yep. Now, if you're a plug-inner, a bunch of them, we will be doing a bunch, like these will continually come up. I'll see if I can find you some more.
Get off me.
Yeah.
Why are we putting 0 at the end?
Because you're trying to make H be 0. You're wanting H. H is the space between the 2 points, and you're wanting that to be 0. So we just manipulated it, canceled out what we could, so that we could plug in 0. Yes.
I'm like looking at my notes and it's showing the same formula for AROC.
Yes.
that's why I'm so confused.
Okay. For AROC, anytime it says average, go to your slope. Yes, that you can find AROC that way. It's a harder way to find AROC, but it shows you how we get to IROC from AROC.
So like, if they're asking for the average, like on the, I guess part A, right? They ask for the average or whatever, then
Delta Y over delta X. Yes.
well, you still have an equation in there, though, right?
Yes.
What about, you know what, never mind.
No, you don't have to stop talking. Are y'all okay? You can, okay. A rock released from rest to fall on a small airless planet falls at y equals gt squared. In t seconds, g is a constant. Suppose that the rock falls to the bottom of a crevice 20 meters below and reaches the bottom in 4 seconds. Find the value of g. So you do it first, then we'll do it together. Well, this is not even a rock right now. Find G. All right, finding G. So look, I am just going to put 20 meters and 4 seconds. I'm going to plug these values in and I'm going to solve for G. That's not hard, right? Say right, because that's right. G times 4 squared. So that would be 16. So that'd be 20 over 16 is G, which is 5 over 4. The whole reason for this is it's just an extra step for you to come up with the equation on your own for this airless planet that we are dropping rocks from. Yes, man. Limits involving infinity. It should have the date on it, man.
That's yesterday.
This is 8/19, or it should. Let me make sure I published it. Yeah. Limits involving infinity. All right, so my equation. It told me A rock released rest to fall on a small airless planet falls y equals gt squared meters. So it gives you the answer in meters. All right, so y equals 5 over 4 t squared. I did that just to come up with that equation. Part B, you're on your own, guys. Part B, try this. Find the average speed for the fall. Find the average rate of speed for the fall. Average rate of speed. I don't even know. I think like y'all smoke crack or something.
I don't know whenever we like somebody threw like a fire extinguisher. We
need to know how many
What did it say? It said in the beginning, let me read it one more time. A rock released from rest to fall on a small airless planet falls y equals gt squared meters in t seconds. G is a constant. Suppose the rock falls to the bottom of a crevice 20 meters below and reaches the bottom in 4 seconds. So what was my elapsed time? 4 seconds. What was your average rate of, I don't know how it worked. Let's try to do it without it. See who can go first. Y'all are so silly. Magic. It's that math magic.
I got 20. Yeah. Go. You got 20. That's wrong. But it said, what is your left? You found out for why.
I actually didn't even have to do that. I could have just gotten it from the beginning of the problem, but it's okay. It is 20. You don't divide by 4 again. This is, so 4 squared is the same thing as 4 times 4, right? If I've got 5 over 4 times 4 times 4, this is over 1. I just canceled one of them out. Okay, so that's not my average rate of change. I was just finding these 2 points. So now my A rock, this is not 20 meters per second. It just falls 20 meters. Is 20 minus 0 over 4 minus 0. So it's 5 meters per second. That's the average rate of change. That's the average speed. Okay. Ready for the next question? Now, how fast, what was the speed when the rock hit the ground? At the instant the rock hit the ground, what speed was it going? No. When t equals what? 4. It hit the ground at 4, so I want I rock at 4. Because I said when it hit the ground. So find the instantaneous rate of change at time 4. What? That y of 4. I plugged 4 in for the. This is saying y of t equals. When you plug it in, all right, so this is just f. So remember my equation is 5 over 4 t squared, right? So this is 5 over 4, 4 plus h squared, minus, I already know what happens when I plug 20 in that equation. I mean, when I plug 4 in. I get 20. I did that in part B, right? You can put, I do at least 0.01. Because it's T plus H for your IROC formula.
Where the square come from?
What?
Where did the square come from?
The formula. 5 over 4 T squared. You've been what now? That's fine. You got what? This is in the limit. You don't have to do that. I would just say the instantaneous rate of change when t equals 4 is 10 meters per second. Find the instantaneous rate of change when t equals 2.5. 2.5. So same process. Let's just make it a little bit harder. Let's say when t equals 2.5, what's the instantaneous rate of change? 10 meters per second. Say again. You plugged a 0. Remember, I want when h equals 0. I did all that because I was manipulating it so that I could substitute 0. If you did not do the algebraic manipulation on the previous one, try to at least do the algebraic manipulation here. The instantaneous, you want to know at what speed was the rock falling at 2.5 seconds. I did make this one a little hard, and I'm sorry. Just because I put the 2.5 in there. And it's not going to play well with the 5/4, but sorry. I'm going to change it to a fraction because I prefer a fraction, but if you prefer to leave it as a decimal, this is grody. You what? I'm going to try. Hopefully the...
It doesn't have to be like exact. It doesn't have to be exact.
Uh, 5/2 plus 5/2 is 10/2, which is 5. Oh, what y'all got? 4, 6, and a 4, 6.25. Yes. Yep. I'm not. I get excited in this class. Now, freak out. I'm like, eh. All right. Yes. We'll just get through a piece of this lesson, but we'll come back to it. So we'll do some more. No worries. Aaliyah, gotcha. All right. Let's do limits involving infinity. Yeah. What is weird? He's always been weird.
What am I doing?
All right. Limits involving infinity. I know.
Why are they here?
They're here like before.
They're going to interview you for your birthday.
They're going to ask you what it's like.
I think it's about our COVID numbers.
Where's are they high? This quarter?
All right.
What are your thoughts? Well,
What did I say?
Without previously low.
What did he say? I wasn't listening. Okay. Changing the subject here. The green graph is a parent graph that you should be very familiar with. What is it?
That's like a what over X, right?
Something over X, you're right.
9.
Just 1 over X. It's not a hard one, y'all. This isn't a hard one. This is just 1 over X. So we're talking about limits involving infinity, and I've kind of touched on it, but we're going to use this for some definitions here in just a second. So I want you to think about this for just a second. Looking at this graph, and I'm going to call this f of x instead of y just to make it a little more. There we go. And I'm going to keep referencing this graph because this is a great graph for us to define some things because it has everything we need. Looking here, what is the limit as x approaches infinity on this graph? Why is it 0? How do you know it's 0? Ironically enough, what's happening at 0? What do you know? An asymptote,
But I have a question.
right?
Why is it not approaching infinity?
It's the y value. Remember, we're looking at what y. Yep. So x is going to infinity. But that's what we're looking for. What is the y value doing?
No, but isn't it like a synonym for it's going to infinity? But y'all are just overthinking.
Carry on. As the graph goes to infinity, as x gets bigger and bigger and bigger, what is y doing? No, you do here. You do. You will use equals. You just have to be careful with equals on certain things. You don't have to worry about that right now. Don't worry about it right now. We'll talk about little things like that later. Yes. So, if I go to negative infinity, it's the same thing. Do you all agree?
I agree with that.
And still there's an asymptote here. So in fact, what we have is we have just defined the term horizontal asymptote in calculus terms. We did. But here, the definition of a horizontal asymptote. If you have a function and you take the limit either as you go to infinity or as you go to negative infinity. If either one of those is some constant, okay, this is an or, not an and, it's or. It only has to happen one way. Then y equals b. And you will have questions. How do you know there's a horizontal? I know there's a horizontal asymptote because the limit as x approaches infinity is a constant. Or if the limit as x approaches infinity of this is bleh, what do you know about the graph? Well, I know that because the limit as x approaches infinity is bleh, that there's a horizontal asymptote at bleh, right? Does that make sense? It's just the definition. That's how we define it.
So what do you mean or?
This is any constant.
So let's get more technical here. When you say or, right? So only one.
Only one of them has to be true. It doesn't have to be both sides of infinity. You can have an asymptote, and y'all know as your graphs get more and more complicated, you can have an asymptote that's just bounding one side of the graph and not the other. And the graph could cross over on this side because asymptotes are not necessarily infinite in both directions. It could just be bounding.
That's kind of like.
Okay? So it kind of is, okay? That's the good thing about this, is it kind of makes sense. So let me give you an example. For example, now, this knowing function transformations is the same graph. The only difference is it's done what? It's up to. That's exactly right. I was thinking up to in there. Okay. Up. Everything goes up to, right? Everything is shifted. Up 2 units, yes? What is the limit as x approaches infinity?
2.
Therefore, have you seen the 3 dots that make a triangle that mean therefore?
Yes, ma'am.
Okay. Therefore,
I really have not, but I know now.
Yes, you have.
I don't think I've seen that
They
before.
said it.
Yeah, we said
She used it like the
The other one's a sweet.
did I? Okay.
I know.
Therefore, y equals 2 is a horizontal asymptote of f of x. Done. It is infinity. I only have to show it one way if I'm proving, if I'd have said negative infinity. I can do both of them. I was just for the sake of example showing you how we justify that there's an asymptote there. Let's look at one that's not so easy to graph, that maybe you have to take out your calculator and pull out that table and look at it, okay? So maybe something like, hey, Miss Redfern?
They're super close friends. She came to my house.
Wait, did she know you before the class?
Show me.
Look at your calculator, take out your calculator, put this in y equals and go to your table and tell me what happens as x gets really, really big and as x gets really, really small. Is it approaching any specific value? Yes, use Princess.
Yeah. Anyways, we're gonna go up one level.
Really?
Right there is 0, 0. Anyways,
Which one?
your mouth.
I just forgot.
That wasn't nice to say.
Wait, so the
That wasn't
asymptote?
nice to say.
Wait, what did you tell us to look at? What x value?
Oh,
wait, what? The asymptote.
Oh, so I need to look at the table, right?
Say that again, Katie.
What value?
Big, big, big values, small, small, small values.
It was so like 0.0001.
Yes.
Negative 0.000.
Yeah, you can talk about other diverse.
I'm sure you know Afghanistan's military becomes diverse and inclusive. So we should find the
Just really, really big. And see if you see it getting close to any number. Mm-hmm.
Hey, are you serious?
I'm gonna at the wall. I'm gonna list where I'm getting.
The graph does some.
It's negative.
Isn't it 1?
Negative 1 and 1.
Wait, mine's like it's hitting 1.
Okay.
It's 1.
Well, you can look at this on the graph.
Your calculator's rounding it to 1, but it's not actually hitting 1. But what you're saying is it's approaching 1.
Yeah, because whatever, like a million.
Well,
Right.
going to infinity it is.
How about negative infinity? Negative 1. Tell me what you can conclude. Therefore,
It's now.
this graph has horizontal asymptotes at -1 and 1.
Wait, but so this limit is
No limit.
not,
It's got no limit.
not the other two, right? It's not the same. Right?
They're not the same.
Yep.
They don't have to be the same. It's an or situation.
No, I'm talking about like.
What we learned yesterday.
There's no limit.
This is not the limit as it approaches infinity from the left or from the right. This is positive or negative infinity. This is the difference in approaching 1 and negative 1. No. No.
So how do you know when it's
So, okay, this is not the same as this.
Oh.
You see the difference?
Yeah.
Okay. Okay, so, right. This is not the same as this. Negative 2 is not the same as 2 from the left. All right. Y'all okay?
No.
Let me just show you sandwich theorem one more time because you're going to have some questions on that. And I will just leave you with all the properties of finite limits are the same as the properties of infinite limits. So I'm going to give you some work. We're going to come in. Don't get bogged down with the property stuff if it gets hard. And I'll post your homework on Canvas whenever I can get. I don't know yet because I haven't looked at it. Yes.
No, that's right.
Right across the
You don't need to pass out. Here's the birthday.
You don't need a pass.
Let's think about this algebraically really quickly. Okay? We know the limit as x approaches 0 of sine x over x. Not as it goes to 0, it's 1. This time I'm going to infinity. A little bit different, right? So I'm going to apply the sandwich theorem to solve this, okay?
No, it's not.
All right, let's think about it. Think about this for just a second. Do you agree? Tell me what sine x oscillates between all the time, a maximum and a minimum. 1 and negative 1. Do we all agree? Negative 1 and 1 all the time. Agree, disagree? Divide everything by x. Okay, I want it to look like this. Now, I do this because I'm looking as I go to infinity. What is the limit as I go to infinity of either one of these? Think about what this looks like.
Oh, it's that thing that we just did. Oh, it's in between this? It's in
1 over x.
gotta be in between.
They're both 0, right? Goodness. Okay. That's if you go, okay, so that is the limit as x approaches 0 of sine x over x. 1. This is the limit as x goes to infinity. All right, so let's think this through for just a minute. This is 1 over x, but remember, if these limits are the same, then I can apply that same limit here because of the sandwich theorem. No, okay, I'm drawing the ends right now. 1 over x, what then does negative 1 over x look like? Just reflected, right? So it's going to be like this and like this. Right, but what for both of those? Okay, so look at this one. What's the limit as x goes to infinity here? It goes to 0. How about this one? What's the limit as x goes to infinity here of negative 1 over x? So the limit and the limit are the same, which means whatever they are has to be the same as this by the sandwich theorem. So therefore, the limit as x goes to infinity of sine x over x equals 0 by sandwich theorem. Yes. As long as that's the same, then the one on the inside is the same. Bless you. Okay, that was Van. Right in front of you. All right.
You didn't put the part about the negative.
About what?
On the bottom part. To limit, as the limit goes, therefore, as the limit goes to x,
I learned a lot.
x goes
It doesn't
from
have to.
equal
It doesn't have to. Okay, so listen, what can I conclude about the graph of sine x over x from this also?
That's not one.
Not only does the limit as x approaches 0 of sine x over x equals 0, but this also tells me what about sine x over 0? If any limit goes to a...
See you on Monday
Yes.
this week. Thank you.
No, it's going to be a horizontal asymptote. Y'all have a good day. See you tomorrow or on Monday.